And see if we can get this to work this time. Third or fourth time I've tried to do this presentation. Tried doing this on other media and I've had to abandon because they wouldn't publish using editing software. So I'm just going to try to run a PowerPoint and see if this works. This is copyrighted to me. Start with an advanced Bohr model. What is an advanced Bohr model? The advanced Bohr model is an expanded model of the traditional Bohr model that includes the Aufbau principle, Hund's rule, Pauli Exclusion Principle within suborbitals. It is meant to be used as a learning supplement to aid in the understanding of atoms' chemistry and its placement within the periodic table. To draw advanced Bohr model, simply start with a circle in the center, represent the nucleus of the atom like you would the traditional Bohr model. Within the center of the nucleus, write the atomic number of the element on top and the number of neutrons on the bottom. Around the nucleus, draw a second circle using a solid line. This represents the first energy level, which contains only one sublevel itself. This would be the same for all elements in period 1, of which there are only 2, hydrogen and helium. To represent the electrons found in an energy level, we use a small circle with an arrow drawn in it. The arrow denotes the direction or spin of the electron. To represent another electron that has paired with the first, we draw the arrow going the opposite direction to show that the electron has an opposite spin from its partner. Only electrons with opposite spins are able to pair up in order to negate the electrostatic repulsion of like-charged particles. Some of the rules covered in this advanced Bohr model. Hund's rule. Hund's rule, every orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin. You'll see how that works as we go along. The Aufbau principle states that in the ground state of an atom or ion, electrons fill atomic orbitals of the lowest available energy levels before occupying higher levels. For example, the 1s shell is filled before the 2s subshell is occupied. In this way, the electrons of an atom or ion form the most stable electron configuration possible. The Pauli Exclusion Principle states that in an atom or a molecule, no 2 electrons can have the same 4 electronic quantum numbers as an orbital can contain, and maximum of only 2 electrons. The 2 electrons must have opposing spins. And as I was mentioned before, since the editing software would not work out here, I'm going to have to do the presentation on my Mac and use the cell phone to try to get this done. So, got a conceptual model here. Imagine the energy levels of electron cloud around the nucleus of an atom like a multi-floor building. The first floor is devoid of furniture, so it has only the ground with no sublevels. The second floor has the floor with 6 chairs, even spaced in the room in pairs, so you may stand on the floor or stand in the chair. This gives you 2 sublevels. On the third floor, you find the floor, 6 chairs spread evenly in pairs about the room, and 5 tables taller than the chairs spread evenly about the room. You can stand on the floor, first sublevel, the chairs, the second sublevel, or on the tables, the third sublevel. You can carry this analogy to the 4th and 5th floors with taller tables. Eventually you get a conceptual analogy that looks something like this. And you see down at the bottom here we have 1s, which has 1 electron pair, and at any s sublevel can only hold 1 electron pair. The 2p level, we go to the second floor, we got a 2s and a 2p, and any p sublevel can hold up to 3 electron pairs, a total of 6. And we'll note later that a combination of the s and p make a total of 8. The third floor, add another sublevel, 3d, they can add up to 5 electron pairs. And as we add sublevels, you end up with 2 more pairs that can be fit in each additional sublevel. That goes 2, 3, 5, and 7, or 1 pair, 3 pairs, 5 pairs, and 7 pairs, and and on up. It gets quite large, so we're just going to stop at the fourth period. The fourth 4 represents the fourth period here. The 2n squared rule. It's a good place to introduce the 2n squared rule, which provides information on the maximum number of electrons that can fit within an energy level, where n is the energy level. For example, for level 1, where n equals 1, we have 2 times 1 squared, which equals 2. For level 2, where n equals 2, we have 2 times 2 squared, which equals 8. For level 3, 2 times 3 squared equals 18, etc. This is related to the increasing number of sublevels as energy levels are added in the three-dimensional nature of orbital geometry, sublevels within levels. Electron configuration shorthand will be demonstrated and used as part of this. Placement of electrons within different energy levels and sublevels can be represented via electron configuration shorthand. If you're teaching, one possible exercise may be to give a student the EC shorthand element from which they draw the advanced Bohr model from. Example from bromine. You see the energy level, the whole numbers represent the energy level. Sublevels by the letters, which I know there's plenty of places to tell you what SP and D stands for. And then the superscript numbers that go along with the sublevel tells you the number of electrons in those sublevels for that particular element. I would suggest as we go on that you have your own copy of the product table. Here's one for reference. As we go along, we're going to go, these are rows. The rows are called periods, and the columns up and down are called groups or families. So we're going to go from left to right along each period, looking at the advanced Bohr model for each of these elements. So first one, hydrogen, found in period 1 in the product table, denoting it has 1 energy level, is found in group 1. The alkali metals, denoting it has 1 valence electron. In the center, we find the nucleus with 1 proton and 0 neutrons. Around the nucleus, we find 1 electron in the first energy level of the electron cloud with 1 sublevel designated 1s. On the left, we see the electron configuration shorthand. The nucleus in the center. 1s only has 1 sublevel, so we don't see the additional sublevel since it only has 1 level. And the Aufbau principle restated here states that in the ground state of an atom or ion, the electrons fill atomic orbitals of the lowest available energy levels before occupying higher levels. For example, the 1s shell is filled before the 2s subshell is occupied. In this way, the electrons of an atom or ion form the most stable electron configuration possible. Helium, found in period 1 of the product table, denoting has 1 energy level, but is found in group 18, the noble gases, denoting has a full and stable outer valence energy level. Since any s sublevel can only hold up to 2 electrons, the element is an exception to the pattern of the remaining noble gases, which have a complete 8 electrons in their outermost energy level. Pauli Exclusion Principle stated again that in an atom or a molecule, no 2 electrons can have the same 4 electronic quantum numbers. As an orbital can contain a maximum of only 2 electrons, the 2 electrons must have opposing spins. That just demonstrates here the arrows are in opposite directions. Lithium. Now we go to period 2. Has 2 energy levels. Is found in group 1. The alkali metals only has 1 valence electron. And we see that there's a dashed line that separates out sublevels. Solid line denotes the outer boundary of an energy level here, and the dashed line the two separating the two sublevels. Beryllium, found in period 2 of the periodic table, denoting it has 2 energy levels. Found in group 2, the alkali earth metals, denoting it has 2 valence electrons. You'll note that the dashed circled line here is what separates the two sublevels. So solid lines separate levels, and the dashed line shows you the separation between the different sublevels. Boron, 2 energy levels, so it is in period 2, has 3 valence electrons. So it's at the top of group 13, which is also known as the boron family. Carbon, placed in period 2, telling us it has 2 energy levels in group 14. Carbon, placed in period 2, telling us it has 2 energy levels in group 14 for 4 valence electrons. Group 14 is also known as the carbon family. And to reiterate Hund's rule, every orbital in the subshell is singly occupied with 1 electron before any one orbital is doubly occupied. On all electrons in the singly occupied orbitals have the same spin. This is a good place to introduce the octet rule involved in both ionic and covalent bonding between atoms. There is a maximum number of 2 electrons that can fit within any S suborbital of a given energy level and 6 electrons within the P suborbital of a given energy level, making a total of 8. Groups 1, 2, and should be 13 through 18 are most energetically stable if the S and P sublevels are maximally filled. The octet rule, adjust this. For some reason this is main group elements are in groups 1, 2, and 13 through 18 tend to gain, lose, or share electrons in order to obtain an energetically stable configuration of 8 electrons and their valence energy levels, consisting of the S and P orbitals. The tendency to lose, gain, or share electrons is dependent on an atom's an atom's electronegativity relative to the atoms is forming a bond with. This can be explained in another video later if there's enough interest expressed in my doing so. Oops, back over here. Nitrogen, found in period 2 because it has 2 energy levels, in group 15 because it has 5 valence electrons. Group 15 is also known as the nitrogen family. Nitrogen, found in period 2 because it has 2 energy levels in group 15 because it has 5 valence electrons. Group 15 is also known as the nitrogen family. And you can feel free to stop and pause the video anytime to see the configurations. We'll start getting partners to these. They're alone, and they all have the same spin up, and they start getting the opposite spins as we move on from here. Oxygen, 2 energy levels, so it's in period 2. Group 16 because this has 6 valence electrons. Group 16 is also known as the oxygen family. Make sure this thing keeps focused. And my daughters are playing around me right now. Trying to be quiet while I do this. Fluorine, period 2, because it has 2 energy levels, and group 17 because it has 7 valence electrons. Group 17 is also known as the halogens. Neon, period 2, because it has 2 energy levels, and group 18 because it has 8 valence electrons. Group 18 is also known as the noble gases. Noble gases are very stable and non-reactive with other atoms because they have complete S and P valence shells. Helium only needs 2 electrons to complete its valence shell since it only has an S energy level, so it is also grouped with the noble gases. So now we got complete 6 and 2, 8 electrons in this valence shell, which is the second energy level. Sodium, found in period 3 because it has 3 energy levels. Group 1 because it has 1 valence electron. Magnesium, found in period 3 because it has 3 energy levels, and group 2 because it has 2 valence electrons. And now you see that the 3s is filled. We'll start filling in the 3p. Aluminum, period 3, group 13 because it has 3 valence electrons. Silicon, period 3, group 14 because it has 4 valence electrons. Phosphorus, period 3, group 15 because it has 5 valence electrons. Sulfur, period 3, group 16 because it has 6 valence electrons. Chlorine, period 3, group 17 because it has 7 valence electrons. Argon, period 3, group 18 because it has 8 valence electrons. Another noble gas, we're going to go to period 4, to potassium, and this is difficult. It's not showing up. Because the angle. So we have our 4s, or 4p, 4d, and 4f sublevels. Four energy levels, so in period 4, group 1 because it's 1 valence electron. What happened to sublevel 3d? Why was it skipped? The 4s sublevel actually has a little lower energy level than the 3d sublevel, so it will be filled first before starting to fill in the 3d sublevel. Calcium, period 4, group 2 because it has 2 valence electrons. Scandium, transition element / transition metal, first of the d sublevel orbital filling elements. Found in group 3 because it has 3 valence electrons, but one of those is in the 3d sublevel. Titanium, period 4, group 4 with 4 valence electrons, 2 in the 3d suborbital and 2 in the 4s suborbital. Vanadium, period 4, group 5. Chromium, period 4, group 6. Note that the electron configuration pattern changes for chromium. It seems to take an electron from the 4s sublevel to finish the 5 half-filled d orbitals. At this point it becomes more energetically favorable to have 5 half-filled d orbitals and a half-filled 4s orbital than 4 half-filled d orbitals and a full 4s orbital. Manganese, period 4, group 7, the 4s sublevel becomes filled once more with an addition of another electron. Iron, period 4, group 8. Iron, cobalt, and nickel are referred to as the iron triad. All three exhibit ferromagnetism. Why are these three out of this period? In an attempt to summarize the explanation, I'll explain it this way. The unpaired electron within the 3d sublevel coupled with the decrease in an atomic radius allows for alignment of the electrons between atoms of these metals so that a magnetic field is generated. Cobalt, period 4, group 9. Nickel, period 4, group 10. Copper, period 4, group 11. As with chromium, it becomes more favorable energetically for the electron to be taken from the 4s sublevel to complete 5 full 3d orbitals. Zinc, period 4, group 12. Gallium, period 4, group 13. Germanium, period 4, group 14. Arsenic, period 4, group 15. Selenium, period 4, group 16. Bromine, period 4, group 17. Krypton, period 4, group 18. And stop there as far as the periodic table progression. We could go on, add more, another sublevel with another level with the sublevels within it. It really gets harder to fit on the screen at that point. Poster paper, or of course a chalkboard or a whiteboard that's large enough. You can get larger, but it's enough. Probably get the point on how this works and combining the different features, way electrons fill the orbitals and suborbitals within an atom. Pause. Now, as far as projects you can do with this, advanced Bohr model construction. As an example, I have element 43, TC technetium. In this particular one, each student was assigned an element. I had them picked random from a couple bits of paper inside that had various elements listed. And I try not to make, if you give a student something like hydrogen to helium while someone else gets something like really large like this, it's not really fair. You want to try to get not have huge differences in the atoms are assigned to do models of this of. Students will make a poster depicting an advanced Bohr model of an atom for that element. Had them each level have their own color so that it make them more distinguishable. Had them, of course, include a key, what energy level and orbital are located, what the key for their electrons, the directions of electrons, and other information of their element. Electron configuration notation, of course, atomic number, mass number, its history and uses, physical chemical properties such as boiling point, melting point, reactivity with elements. Some of them as a modification, accommodation. I had them, construct it using a computer printout, coloring tape, glue poster, and this as a modification accommodations for some students. That's the electron configuration for it, or shorthand. And then this particular one, I had them click and drag the electrons into the correct location according to the EC shorthand. So this was an accommodation, for students that couldn't complete the other assignment the way it was written for whatever reason. Hopefully this comes in useful for college students taking chemistry, these particular concepts, high school students. I've even used this to teach this to
middle school students when they're learning about the periodic table and certain other concepts, but mainly chemistry high school students. Hopefully this was helpful. If you liked it, please hit the like and the subscribe button, and I'll try to get more content out. Any constructive feedback would be appreciated. Anything unreasonable, of course, I'll delete if it's just someone being ugly. Anyway, thank you for your time and attention.